Our last bit of learning about Lewis diagrams to do with ions, specifically polyatomic ions. So ions that have, on the whole, gained electrons. Now it could be something like ammonium where it's lost an electron as well, but most ones you'll come across are anions. There's not that many polyatomic cations. So the two I've got here are two examples that aren't just really straightforward. They needed a bit of work to get right. So I'm just going to walk you through those. So the first one is carbonate. Now using my way of doing this, what I do is I add up my number of valence electrons, 4 for carbon, 6 for each oxygen, but I've also got to take into account the charge. It's 2 negative, so it has 2 more electrons in its total number of electrons. So it's going to have not 22, but 24 electrons. So carbon's got a higher valency than oxygen, so I put it in the middle. I put each oxygen around it. I use bonding pairs to join them. And then I make each oxygen obey the octet rule. And I find that uses up my 24 electrons across those 3. But carbon isn't obeying the octet rule. So what I do is I move a lone pair into here to become a bonding pair. So it looks like this. And then the last thing I do is I put square brackets around my Lewis structure and I put the 2 negative charge there. That shows that it's not a molecule, but it is an ion. This one I've used because it shows you that polyatomic ions don't always have single bonds. Sometimes they have double bonds as well. So be aware of that. Use your rules that you use for drawing Lewis diagrams for ions the way that you do with molecules. The difference is at the end, put the square bracket around it and the charge. The other thing to keep note of is include those electrons in your total of valence electrons. So let's look at I3-, which is a pretty tricky one. And it's a tricky one because it doesn't seem to work. It doesn't seem to have space for enough electrons. So what I've done here, and I haven't quite finished this so I can work you through it, is I've gone, okay, there's 3 iodines. They each have 7 valence electrons. So that's 21, plus the 1 for the negative charge is 22. They're all iodine. Who cares which one goes in the middle? So I'm just going to put them in a row like this. So I've got an iodine in the middle and 2 on the outside. I've bound them. So I've got my bonding pairs here. Then I've completed the octet rule for the outside ones. When I add all these up, 2, 4, 6, 8, 10, 12, 14, 16, I've still got 6 left. Now what I'd normally do then is put some more in the central one. And now I've got 2 electrons left. So I've got to add 1 more pair of electrons somewhere. Well, iodine, being a lot further down in the periodic table, doesn't use its 3d orbital, but it actually uses, now I've got to try and remember here where iodine is, I think it's the 5d orbital that it's using. So it can actually expand the octet. So it can have 2 more in here. This other pair can go to the central atom here. Again, this is the same as the rules we were using before for extended octet. We extend the octet, expanded octet. We expand it for the central atom only, not for one of the ones on the side. So it will end up looking like this. Then I put my square brackets around it to show that it's an ion and put the ion charge there. The reason I've written sulfate and phosphate up here is these seem to work this way. They don't seem to need to have expanded octets. But because sulfur is bound to 4 things, when its valency is only 2, it actually has to have either a valency of 4 or 6. What you find is that this one has 2 double bonds and 2 single bonds. Phosphate, same thing, the valency is only 3 of phosphate, but it's bound to 4 different things. So what we find is that it's using its d orbital, its 3d orbital, so therefore there's at least 1 double bond in that one. Those are ones worth having a look at yourself and maybe get me to check your answers to see if they are correct.